Chernoff Bounds. In section 13.3, we defined the expectations of a random variable formally and have worked with these definitions and its consequences ever since. Intuitively, we have a sense that the value of a random variable ought to be near its expectation with a reasonably high probability, but we have not yet explored the extent to which this is true. We now turn to some results that allow us to reach conclusions like this, and then see a sampling of the applications that follow. We say that two random variables x and y are independent if for any any values I and j, the events probability such that x is equals to I and the probability such that y is equals to j are independent. This definition extends naturally to larger sets of random variables. Now consider a random variable x that is a sum of several independent 0-1 valued random variables. X equals to x1 plus x2 plus x3 and so on plus xn, where xi takes the value 1 with probability pi and the value 0 otherwise. By linearity of expectation, we have the expectations of x equals to the summations of pi summing with index starting from 1 to n. Intuitively, the independence of the random variables x1, x2, and so on to xn suggests that their fluctuations are likely to cancel out, and so their sum x will have a value close to its expectation with high probability. This is in fact true, and we state two concrete versions of this result, one bounding the probability that x deviates above expectations of x, the other bounding the probability that x deviates below expectations of x. We call these results Chernoff bounds, after one of the probabilists who first established bounds of this form. 13.42. Let x, x1, x2, and so on to xn be defined as above, and assume that mu is greater than or equals to the expectations of x. Then for any delta greater than 0, we have the probability of x greater than 1 plus delta times mu, which is less than e to the delta divided by 1 plus delta to the 1 plus delta, then to the mu. Proof. To bound the probability that x exists 1 plus delta times mu, we go through a sequence of simple transformations. First, note that for any t greater than 0, we have the probability of x which is greater than 1 plus delta times mu, which is equals to the probability of e to the t x, which is greater than e to the t times 1 plus delta times mu. As the function f of x is equals to e to the tx is monotone in x, we will use this observation with a t that we will select later. Next, we use some simple properties of the expectation. For a random variable y, we have gamma, such that the probability of y which is greater than gamma is less than or equals to the expectations of y by the definition of the expectation. This allows us to bound the probability that y exceeds gamma in terms of expectations of y. Combining these two ideas, we get the following inequalities. The probability of x which is greater than 1 plus delta times mu is equals to the probability of e to the tx which is greater than e to the t times 1 plus delta times mu, which is less than or equals to e to the minus t times 1 plus delta times mu, then times the expectations of e to the tx. Next, we need to bound the expectations of e to the tx, writing x as x equals to the summations of xi, summing for index I. The expectation is the expectations of e to the tx, which is equals to, if we expand the definition of x, which will be equals to the expectations of e to the t times the term in the exponent, that is the summations of xi, summing for index I, which is equals to the expectations of the multiplications of e to the t times xi, where the multiplication is taken among all possible I. For independent variables y and z, the expectations of the product yz is the expectations of yz equals to the expectations of y times the expectations of z. The variables xi are independent, so we get the expectations of the multiplications of e to the t times xi multiplying for all possible I is equals to, if we take out the multiplication symbol, there will be the multiplications of the expectations of e to the t times xi, where the multiplication is taken among all possible index I. Now e to the t times xi is e to the t with the probability pi, and e to the 0 equals to 1 otherwise, so its expectation can be bounded as the expectations of e to the t times xi, which is equals to pi times e to the t plus 1 minus pi, which is equals to 1 plus pi times e to the t minus 1, which is less than equals to e to the pi times e to the t minus 1, where the last inequality follows from the fact that 1 plus alpha is less than equals to e to the alpha for any alpha greater than equals to 0. Combining the inequalities, we get the following bound. The probability of x greater than 1 plus delta times mu, which is less than equals to e to the minus t times 1 plus delta times mu times the expectations of e to the t times x is equals to e to the minus t times 1 plus delta times mu times the multiplications of the expectation of e to the t times xi, where the multiplication is among all possible index I. Here we show that from the last two lines of the screen. To obtain, and which is equals to less than equals to e to the minus t times 1 plus delta times mu times the multiplications of e to the pi times e to the t minus 1, where the multiplication is taken among all possible I, which is equals to, if we expand the expectation, the multiplication, there will be e to the minus t times 1 plus delta times mu times e to the mu times e to the t minus 1. To obtain the bound claimed by the statement, we substitute t equals to ln of 1 plus delta, where 13.42 proved an upper bound, showing that x is not likely to deviate far above its expectation. The next statement, 13.43, provides a lower bound, showing that x is not likely to deviate far below its expectation. Note that the statements of the results are not symmetric, and thus makes sense. For the upper bound, it is interesting to consider values of delta much larger than 1, while this would not make sense for the lower bound. 13.43. Let x, x1, x2, and so on to xn, and mu be defined as above. Then for any 1 which is greater than delta, greater than 0, we have the probability of x which is less than 1 minus delta times mu, which is less than e to the minus 1/2 times mu times delta squared. The proof of 13.43 is similar to the proof of 13.42, and we do not give it here. For the applications that follow, the statements of 13.42 and 13.43, rather than the internals of their proofs, are the key things to keep in mind.